My name is Iossif Papadakis. I am an astronomer and I work as an associate professor at the physics department of the University of Crete. I'm also a senior researcher at the Skinakas Observatory, which is located on the island of Crete in Greece. My main area of research is observational extragalactic astronomy. In this video presentation, I will show you how to use CCD images of elliptical galaxies in order to classify them. Before doing so, I will give you a short introduction where I will present you the process of scientific exploration that has led to our present-day knowledge about galaxies. The name galaxy is from the Greek word galaxias. The word was meant to describe the pale band of light formed by the galactic plane as seen from Earth. According to Greek mythology, Zeus, the father of all gods, placed his son Heracles on Hera's breast while she was asleep for the baby to drink her divine milk. Hera woke up while breastfeeding, and as she pushed away this unknown to her baby, a jet of milk sprayed the night sky, hence producing the Galactico Κύκλο, or the Galaxia, that is our own Milky Way. Even from ancient times, a few people, like for example the Greek philosopher Democritus in the 5th century BC, thought that the diffuse light of the Milky Way may be produced by thousands of stars. However, actual proof of the Milky Way consisting of many stars came much later, in about 1610, from Galileo Galilei. Galileo was the first scientist who used the telescope to observe the night sky systematically. Among other celestial objects, Galileo also observed the Milky Way and found it to be a multitude of stars, packed so densely that they appear to be like bright clouds seen in the night sky from Earth. In the 18th century, Thomas Wright, an English astronomer and mathematician, and Immanuel Kant, a German philosopher, in order to explain the circular distribution of the Milky Way across the heavens, proposed that the galaxy might be a massive, rotating stellar disk, held together by gravitational forces. The first attempt to describe the shape of the Milky Way and the position of our solar system in it was carried out by Sir William Herschel, a German-born English astronomer, towards the end of the 18th century. Herschel's map of the Milky Way was based on counting the numbers of stars he could observe in many regions of the sky. Based on this data, Herschel concluded that our Sun was close to the center of the Milky Way, and that the radius of our galaxy was approximately 5 times greater than the vertical thickness of the galactic disk. At the beginning of the 20th century, the Dutch astronomer Jacobus Cornelius Kapteyn essentially confirmed Herschel's model of the galaxy, again using the technique of star counting. According to his model, the galaxy was a lens-shaped universe of stars whose density decreased away from its center. However, through the use of more quantitative methods, he was able to also specify a distance scale for his model of the galaxy. He estimated that the galactic radius was approximately 30,000 light-years in size, and he also found that the Sun was relatively close to the galactic center, no more away than 2,000 light-years. We know today that both Herschel and Kapteyn were in error for a simple reason. They had assumed, among other things, that there is nothing between the stars to obscure them, hence they could see to the edges of the galactic stellar distribution. In other words, they had failed to include in their distance estimates the effects of interstellar extinction due to dust and gas. In fact, Kapteyn's selected regions to measure stars were largely within the galactic disk, where extinction effects are most severe. As a result, he was unable to see the most distant portions of the Milky Way, causing him to underestimate its size and the location of our solar system in it. During the years between 1915 and 1919, shortly before Kapteyn's model was published, Harlow Shapley, an American astronomer, estimated the distance to many globular clusters using the period luminosity relation for some variable stars like the so-called RR Lyrae stars. Since these stars are easily identified in the clusters through the periodic variations in their luminosity, it is relatively easy to estimate their distances and those of the clusters in which they reside from the Sun. In analyzing his data, Shapley recognized that the globular clusters are distributed not around the Sun, but in a region of the sky that is centered in the constellation of Sagittarius, at a distance that he determined it to be 40 to 50,000 light-years from the Sun. Furthermore, he estimated that the most distant clusters are more than 180,000 light-years beyond the center. By assuming that the extent of the globular clusters was the same as the rest of the galaxy, Shapley believed that the diameter of the galaxy was of the order of 300 to 320,000 light-years, almost 5 to 6 times the value proposed by Kapteyn. We know today that Shapley was also in error in some of his calculations. In fact, errors in the calibration of the period luminosity relation of variable stars, due to effects of interstellar extinction that were not taken properly into account, led to an overestimation of the distances to globular clusters, hence to an overestimation of the size of our galaxy. Nevertheless, the work of astronomers like Shapley made us realize, almost 100 years ago, that our galaxy is really big and our Sun is not located at its center. We have reached what we believe to be a true understanding of the nature of the Milky Way only the past 2 or 3 decades. We now know that the Milky Way light comes mostly from stars distributed in a flattened disk-like structure, some 100,000 light-years across. Our Sun is located very close to the galactic plane, approximately 25,000 light-years away from its center. At the center of our galaxy lies a mysterious radio source called Sagittarius A, which we now believe it is associated with a massive black hole, whose mass is 2 to 4 million times the mass of our Sun. We also know that, in addition to stars, the Milky Way contains gas and dust. Perhaps most astonishingly of all, we now believe that the stars, the gas and dust account for no more than about 10% of the total mass of the Milky Way. Most of its mass, approximately 1 trillion times the mass of our Sun, is in some kind of unidentified form of matter known as dark matter. In fact, the term Milky Way is now applied to this whole collection of entities, the whole system of stars, gas, dust, and dark matter, and not just to the diffuse band of light of ancient Greeks, which was resolved by Galileo some 400 years ago. Having understood the shape, size, and contents of our own galaxy, it seems natural to ask the question, does anything exist beyond the boundary of our galaxy? And although the answer now is a definite yes, this was not always the case in the past. People had noticed many centuries ago that, apart from stars, there are also some fuzzy patches of light in the sky that cannot be resolved into a clear ensemble of stars when observed by naked eye or even through a small telescope. Thomas Wright in the 18th century speculated that some of these nebulae might be separate Milky Ways, and Immanuel Kant introduced the term island universe for these distant nebulae. An important discovery was made in the middle of the 19th century. In 1845, William Parsons, a British lord, built in Ireland what was then the largest telescope in the world, with a diameter of 1.8 meters. Parsons carried out pioneering astronomical studies, and he was able to resolve, for the first time, the spiral nature of some nebulae, today known to be spiral galaxies. Their pinwheel appearance strongly suggested that these spiral nebulae may be rotating. The first spiral galaxy he detected was M51. today known as the Whirlpool Galaxy, and his drawings of it closely resemble modern photographs. The true nature of some of these nebulae remained in question until the beginning of the 20th century. The argument over their nature centered on their distances from us and the relative size of the galaxy. The debate as to whether they are members of our own galaxy or separated from it was finally settled in 1923, when Edwin Hubble was able to resolve the outer parts of some spiral nebulae as collections of individual stars, using the new 2.5-meter telescope at Mount Wilson in the US. More importantly, though, he was able to identify some Cepheid variables in M31, the Andromeda Galaxy. By measuring the period of their variations, he was able to determine their luminosity via the period-luminosity relation that Henrietta Leavitt, a female American astronomer, had established a few years earlier. It was then a matter of measuring the apparent magnitudes of the Cepheids in order to estimate the distance of the Andromeda Nebula from the Sun. Although his original value of 1 million light-years is about 3 times smaller than the modern estimate, it is still good enough to show definitely that the spiral nebulae are indeed island universes, just like our own Milky Way. Hubble's discovery was announced on January 1, 1925, and it fundamentally changed our view of the universe. To summarize, it was not until the second decade of the last century that we finally realized that our solar system is not located near the center of the Milky Way, that our galaxy is a finite-sized, disk-like system of stars, and that it is only one of a countless number of similar stellar systems in the universe. And it is fair to say that this knowledge constituted an advance in our understanding of the universe comparable to that of the Copernican revolution. As soon as the extragalactic nature of the galaxies had been established, work began on determining their physical properties and classifying them accordingly. Once again, Hubble played a key role. He was the first who tried to set out a scheme for classifying the galaxies. In his book, The Realm of the Nebulae, published in 1936, he established a classification system which, including some later additions and modifications, it is still in use today. Hubble recognized 3 main types of galaxies: ellipticals, lenticulars, and spirals, with a 4th class, the irregulars, for galaxies that would not fit into any of the other categories. Elliptical galaxies have an ellipsoidal form. They are smooth and they are almost featureless, devoid of structures like spiral arms and dust lanes. They are lacking in cool gas and, as a result, they have few young blue stars. Ellipticals predominate in rich clusters of galaxies. The largest of them, the so-called CD galaxies, are found in the densest parts of those clusters. These systems can be up to 100 times more luminous than our Milky Way. Normal, or giant ellipticals, have luminosities a few times that of the Milky Way, with characteristic sizes of tens of kiloparsecs. A kiloparsec is the unit of length that astronomers use and is equal to approximately 3,200 light-years. The stars of the bright ellipticals show little organized motion, such as rotation. Their orbits about the galaxy center are oriented in random directions. Lenticular galaxies are labeled SO, and they form a transition class between ellipticals and spirals. On one hand, they generally lack massive quantities of gas and dust, and they prefer regions of space that are fairly densely populated with galaxies, like ellipticals. On the other hand, they also have a thin and fast-rotating stellar disk in addition to the central elliptical bulge, like spirals. Spiral galaxies are named for their bright spiral arms, especially prominent in the blue light. The arms are outlined by clumps of bright, hot, young O and B stars, and the dusty gas out of which these stars form. About half of all spiral and lenticular galaxies show a central bar. The barred systems form a sequence parallel to that of unbarred galaxies. Along the sequence from the SA to the SC spirals, the central bulge becomes less important relatively to the disk, the spiral arms become more open, the fraction of gas and young stars in the disk increases, the luminosity decreases, and the speed at which the disk rotates decreases as well. Consequently, the galaxies are less massive. Hubble placed all galaxies that did not fit into his other categories in the irregular class. Today, we use that name only for the small blue galaxies which lack any organized spiral or other structure. The smallest of the irregular galaxies are called dwarf irregulars. Back in the 20s, Hubble continued discovering Cepheid variable stars in spiral nebulae. These discoveries enabled him to calculate the distances to these objects. Combining his measurements of galaxy distances with measurements of the redshifts associated with the same galaxies, measurements which were made by Visto Slipher, an American astronomer, Hubble discovered a rough proportionality between the redshift of an object and its distance. If the galaxy redshift could be attributed to the Doppler effect, then Hubble's discovery could only mean one thing: the universe is expanding. The galaxy is rushing away from us, and their recession speed is larger for more distant galaxies. The relation between the recession speed and the galaxy distance is now known as the Hubble Law. Using this law to find approximate distances for galaxies, we can examine their distribution in space. Our Milky Way and its neighbor Andromeda form part of a small group of 30 galaxies or so, which is called as the local group, and covers a region of space which is 10 million light-years in diameter. Even more distant galaxies are not spread uniformly in space. They lie instead in string-like filaments. At the intersection of the filaments are complexes of rich clusters with thousands of galaxies in each of them. Large regions between the filaments are almost empty of bright galaxies. These voids are typically many tens of millions of light-years across. This distinctive galaxy distribution pattern makes us wonder, why and how did this happen? In general, questions like how and when did galaxies form, and what are the physical factors that determine a galaxy's morphological pattern, are the subject of intense research effort at the moment. We do not have definite answers yet, although some patterns are beginning to emerge in the still unknown territory of galaxy formation and evolution. However, this is an enormous topic which is beyond the scope of this video presentation. So, let us now start preparing ourselves for the tutorial that I mentioned at the beginning of this demonstration. The traditional galaxy classification criteria have been based on the visual examination of a relatively small number of galaxy images, which were usually taken in the B or photographic band. Furthermore, most of the prototype galaxies whose images were used to define the classification criteria were rather luminous galaxies that are actually not typical of the general galactic population in the universe. Finally, most published galaxy classification schemes are the result of a subjective assessment of a picture by a human being. In fact, it is not unthinkable that two astronomers will place the same spiral galaxy in different, albeit adjacent, classes. But this is not usually the case with ellipticals, as there exists an objective way to classify them. According to the Hubble classification scheme, ellipticals are classified by the letter E, followed by an integer number, say n, which represents their degree of ellipticity on the sky, and is determined by the ratio of the minor to the major axis of the galaxy's isophotes. The number n depends on both the intrinsic shape of the galaxy as well as the angle with which the galaxy is observed. For a spherical galaxy with A equal to B, the number n is 0, while for more elongated systems, n is greater than 0. The maximum value of n, in reality, is about 7, and the most common shape in elliptical galaxies is close to E3. We mentioned above the word isophotes. An isophote is a contour of constant surface brightness on a galaxy image, while the surface brightness of a galaxy at a point which is located at a distance r from its center is determined by the amount of light per unit area that we receive from around this point. Now, having defined the way elliptical galaxies are classified and given the necessary definitions, we're ready to start working with the real data. This is the CCD image of the galaxy NGC 5982, which is an elliptical galaxy in the constellation of Draco, at a distance of approximately 145 million years. It probably hosts a supermassive black hole at its center, which is mildly active as well, but we will not deal with this issue here. The image you see was taken by the 1.3-meter telescope at Skinakas Observatory in the V-band. The image has already been debiased and flat-fielded. Our first task will be to classify this elliptical galaxy using this image and IRAF, which is a general-purpose software system for the reduction and analysis of astronomical data, written and supported by the IRAF programming group at the National Optical Astronomy Observatories in the US. The starting point of the tutorial is the IRAF directory where the file login.cl is located. And I start up IRAF by typing cl. Then I go to the directory where the data are stored, and I make sure that the CCD image file of the galaxy is there. To see the image, I will use the DS9 astronomical imaging software package, which is developed by the Smithsonian Astrophysical Observatory in the US, and the display command in IRAF. I place the cursor on the image, and I press the right-hand button of the mouse. By moving the cursor across the image, I can change its contrast, and in this way I can get a first impression of the size of the galaxy. To get a more quantitative measure of the galaxy dimensions, I will use the IRAF command imexamine. By moving again across the image the cursor, I press the button M on regions of the CCD which are free of stars and away from the galaxy. By doing so, a list of numbers appear on the IRAF terminal, which give information about the CCD area directly below the cursor position. The first column lists the cursor position in pixels, and the third one gives us the intensity in CCD counts of a small rectangular area of size 5 by 5 pixels centered around the cursor position. In our case, the mean of all these values is around 415 counts, a number which represents the average sky intensity on the image. Using again the command imexamine, I can now get the radial profile of the galaxy intensity. To do so, I move the cursor on a position close to the galaxy center, and I press the button R. The intensity radial profile now appears. This plot shows how does the galaxy emission change with distance. The x-axis shows the distance in pixels from the galaxy center, while the y-axis shows the average intensity in counts of all pixels at the same distance from the center. The galaxy light emission drops very rapidly from a maximum value of about 17,000 counts to almost 1,000 counts at a distance of just 18 pixels, which for this image corresponds to about 15 arcseconds on the sky. In such cases of rapid changes of the light intensity, it is advisable to replot the radial profile using axes on a logarithmic scale. It will also be helpful to plot the profile at larger distances as well, to investigate when it reaches the background sky level. This distance will give us an approximate indication of the actual size of the galaxy. To produce the new plot, I have to change the default settings of the command imexamine. This can be done with the use of the command epar. First, I change the maximum size of the plotting radius of the x-axis from 18 to 300 pixels. Then, I change the scale of both the x and y axes from linear to logarithmic. Since both axes now are on a logarithmic scale, I also change the lower x and y axis plotting window limits to 0 and 100 respectively. I'm now ready to reproduce the galaxy profile using once more the command imexamine. The new profile looks approximately linear now, and we can see that the galaxy intensity becomes comparable to the sky level at a distance of about 100 pixels from the galaxy's center. The spikes on the right-hand side show the radial profiles of foreground stars of our own galaxy, which are located by chance close to the image of NGC 5982. Notice how much narrower these profiles are in comparison to the galaxy profile. Above the radial profile plot, there are two numbers which indicate the position of the galaxy center, which in our case it is roughly located at the pixels 510 and 510 along both the x and y axis. These numbers will be used in our next step. Remember that our main task is to classify the galaxy, and that to do so we have to measure the length of the major and minor axes of the galaxy isophotes. So first we have to determine these isophotes. Luckily, this can be done easily with the IRAF command contour. This command will automatically draw a plot with the lines of constant intensity on the galaxy image. That is a plot of the galaxy isophotes, exactly as needed. So let us try this command. Since the galaxy center is located at the position 510 and 510 on the CCD, and its radius is about 100 pixels, we will plot the isophotes on a rectangular region of the CCD image, centered on the galaxy and with a size of 200 pixels on each side. The resulting contour plot looks a bit crowded. So let's try to redo it by forcing the value of the lowest intensity contour to be just above the sky background level. This can be achieved by using the command epar to change the value of the floor parameter of the contour command to 500, for example. The new contour plot looks a bit better now, but we can still improve it by choosing the ceiling parameter of the contour command to be 1000. In this way, we can produce a plot of the outer region isophotes of the galaxy. The contour plot is now much better. The first thing to notice is that the contours have an elliptical shape exactly as expected. Furthermore, we can also see that the position of the center and the direction of the long and small axes of the isophotes remain rather stable from the inner to the outer ones. This will make our task of classifying the galaxy rather easy. Let us now produce a plot of the inner isophotes of the galaxy. To this end, we change the floor and ceiling parameter values to 1000 and 10,000 respectively. We also change the size of the image section around the galaxy center to be smaller, approximately 70 pixels on each side. The new contour plot looks just fine. Even the inner region isophotes have an elliptical shape, which remains the same for all of them. More importantly, their direction is similar to the direction of the outer region isophotes and remains remarkably stable. All we need now is to measure the length of the major and minor axes of an isophote to classify the galaxy. But which one of the contours should we use? As it is often the case in experimental physics, the best approach is to choose a few well-defined contours, measure the length of their major and minor axes, estimate their ratio b over a, and then take the mean of all the b over a ratios as our final estimate of the galaxy's ellipticity. So I run again the contour command by changing the n contour parameter to 2 to have fewer contours on each plot. First, I will create the contour plot for the inner region of the galaxy. Notice that this time I run the command with the device name being changed to EPSF, so that the Iossif plot will be saved onto a PostScript file. And then I repeat the same procedure for the outer region of the galaxy by changing again the floor and ceiling parameter values accordingly, and by increasing once more the region of the CCD. Let us now examine the plots that I just created. Here is the plot for the inner region contours, and here is the plot for the outer region. There are 3 isophots on each plot. I can print them, and I can measure the length of the major axis A and the length of the minor axis B of each contour on the plot, and then calculate the corresponding B/A ratios. Here is a list of my measurements. Their mean value is 0.68, which implies that n is equal to 3.2, or, when rounded to the nearest integer, n is equal to 3. Hence, NGC 5982 is an E3 elliptical galaxy, and this is the major result of our exercise. Okay, that was it all. In this presentation, I gave you a short introduction on the subject of extragalactic astronomy, and I showed you an example of how astronomers today can use the CCD images to measure the properties and extract quantitative information about these magnificent objects of the cosmos that we call galaxies. I hope you enjoyed the presentation and that you got an idea about the working methods of modern-day astronomers.